This is a lecture on the strategic voting model. So the theme that we are exploring in this part of the lecture is the wisdom of crowds. We're going to explore Condorcet's theme that larger decision-making bodies make better decisions on average compared to smaller bodies or judges. And also that as the jury size gets very large, the probability of the jury making a mistake approaches zero. So the question is, under what kind of situations these consequences come about. So let me lay it out for you, the outline of a very simple voting model. So a group of people or a society, they're going to make a binary decision. They can choose one option or the other. There are two options. You can think of, a country voting whether to adopt free trade or remain behind tariff walls, or, for example, Britain voting whether to remain in the European Union or to leave it. So these are the kinds of decisions we can have in mind. Throughout, we'll use the metaphor of a jury trial. So in a jury trial, what happens is that the defendant is either convicted or acquitted. These are the two decisions available, and the jury has to collectively decide one of the two. The jury metaphor is not that good a fit, because in the model that we're going to describe, the assumption is going to be that the jury members or the voters cannot talk to each other, which is not quite true in actual jury trials. But nevertheless, given the history of this sort of discourse, we will adopt the metaphor of the jury trial. So in that language, let me describe the model for you, but keep in mind that the applications of the model is much wider ranging, and it probably applies better to larger elections with anonymous voters, people who don't know each other and cannot talk to each other. Okay, so here's the outline of the model on this slide. There are two possible decisions, C or A. C stands for, let's say, conviction, A stands for acquittal. And there is a state of the world which can take one of two values, I or G. I stands for innocent, G stands for guilty. So the defendant is either truly guilty or truly innocent, and one of the acquittal or conviction decisions have to be taken. So the jurors' preferences are a function of both the state of the world and the decision that they adopt. And the idea is that if the defendant is actually guilty, then the correct decision is C. And if they manage to take the correct decision, they'll get a payoff of 0. That's just normalization, right? 0 is the highest payoff that will obtain. And similarly, if the state of the world is innocent, I, then the correct decision would be acquittal. So, and that again would give 0. Now, there are two kinds of mistakes that the jury might make here. The first mistake is that they convict an innocent defendant, so that's the first line here. In that case, they suffer a cost of Q, or a payoff of minus Q. The other kind of mistake is to acquit a guilty defendant. They ideally don't want to do that. And if they commit that mistake, then their payoff is minus 1 minus Q. So 1 minus Q is the cost that they suffer in that case. So the idea is that the two kinds of errors may have different moral consequences. They may worry the jurors or the voters differently. So that's why we allow for different values of Q and 1 minus Q. And so this is a general parameterization. One assumption, notice that I have not put I subscript to Q. So all the jurors care about the two types of errors in the same way. So there is perfectly common preferences. So if the jurors all had the same information, they would agree about what is to be done, whether conviction or acquittal is the right decision. But they're sitting in their separate rooms and have to cast their votes by themselves without consulting others. So Q is a fraction. Q is a number between 0 and 1. And if you do the maths, you will find, and I have done this before, I'm just reviewing the last part of what we did in class, Q turns out to be the threshold of doubt. So after processing all information and updating beliefs, if a juror feels that the probability of guilt is Q or more, then the optimal decision for the juror would be to convict. And if it's the probability of guilt is less than Q, then the optimal decision will be acquittal. So that's something that you can check, and you should just check yourself very quickly. Okay, so Q serves as the threshold of doubt, right? So all the action depends on whether after processing information, the belief about guilt crosses Q or not. And we have to start with some prior belief on guilt. We will take that prior on guilt to be pi. This pi will be updated using Bayes' rule as we go along. Okay, so now let's get to the last bit of the description of the model. We are going to assume that all the voters get a private signal about the state of the world, whether the defendant is guilty or not guilty. Now, the signal TJ is juror J's signal. It takes one of two values, small g or small I. These are the two possible values. And this 2 by 2 matrix is the conditional probability distribution. So it tells us what is the probability of receiving either signal when the true state is guilty and when the true state is innocent, right? So when the true state is guilty, P sub G is the probability that the guilty signal will be emitted. So 1 minus PG is the probability that the wrong signal will come through under a guilty state. Now, in most of the applications that we are going to do, we'll make this probability matrix symmetric. I've written it out in a very general form, but generally we will set PG equal to PI, equal to some number P. So the probabilities will be flipped around as we go from the upper row to the lower row. And in general, the signals are informative if the two rows are not identical, right? So that means that after looking at the signal, the voter learns something about the possible state of the world and will revise her belief starting from the prior pi. As I said, voters cannot communicate, so they have to vote independently. And also, given that everybody has the same Q, there is common interest among the voters, fundamentally. At bottom, they have the same objective function. So if we allowed for communication, the game would be quite trivial. A little bit of terminology. First of all, game theoretically speaking, the voting strategy of each voter is a mapping going from signal to the votes for either conviction or acquittal, right? So it goes from this set, G and I, to all probability distributions over a conviction vote and an acquittal vote. So we are going to allow for mixed strategies. Sometimes a voter may randomize between voting for conviction and voting for acquittal. Now, here are three terms which I want to just lay down. First, informative voting. What is informative voting? Informative voting is when the voter adopts a pure strategy. When she sees a guilty signal, she votes for conviction. When she sees an innocent signal, she votes for acquittal. That's informative voting. Now, a weaker form of informative voting is responsive voting. Responsive voting is where the probability of voting for conviction, this VG, is different from the probability of voting for conviction when the signal observed is I. So these are probabilities of voting for conviction after seeing the guilty signal and after seeing the innocent signal. If these probabilities are different, that means, at least to some extent, probabilistically speaking, the voter is influenced by the signal that she has observed, right? So that's what we're calling responsive voting. So as you can see immediately, informative voting is a special case of responsive voting. Responsive voting is more general. And finally, sincere voting. Sincere voting is when a voter's strategy is as if she was the lone decision maker, as if the jury size is 1. Whichever way she would have voted if she were the only member of the jury, that's exactly how she votes with many other members. If that is true, then we'll call that sincere voting. So informative, responsive, and sincere. Okay, so moving ahead, let me walk through an example, a numerical example, which will give you some idea about how to mathematically solve for the equilibrium, the perfect Bayesian equilibrium of a voting game like this, and also some of the conceptual elements, especially related to Condorcet's questions, whether a jury does better than a judge, whether a very large jury makes almost perfect decisions. Those are the questions that we'll begin to see addressed in this numerical example. So, the numerical example has 2 voters. It's the simplest possible case we can think of. The threshold of doubt will take to be half. So Q equal to half. So the 2 errors, convicting the innocent and acquitting the guilty, carry equal moral cost in this example. And the prior on guilt we will take to be 2/3, pi equal to 2/3. And the accuracy of the signal, remember that conditional probability matrix, accuracy of the signal is 3/4. So whatever be the underlying state of the world, there's a 3/4 probability that the signal will truly reflect that, and there's a 1/4 probability that the signal will actually be misleading. So these are our parameters values that we have taken for this general model. So first, as a starting point, let's think of the case of a judge, a single decision maker. So n equal to 1, right? Only one person will observe the signal and choose either conviction or acquittal, the only decision maker around. Okay, so there are 2 conditional probabilities that we have to calculate. What is the posterior probability on guilt, on capital G, given that the signal is small g, the signal is a guilty signal? And what is the posterior probability on guilt given that the signal is an innocent signal, right? Now, these are Bayes rule formula. When the signal is guilty, if we apply Bayes rule, and it's pretty simple, you've been doing this sort of Bayes rule calculation throughout this course. When you calculate, plug in the values that we have taken, we get 6/7. So basically, you start with a prior of 2/3 on guilt, and if the signal turns out to be guilty, then no wonder that the posterior belief will get a bump. It'll rise from 2/3 to a higher value, which turns out to be 6/7. And this is strictly greater than half. Half is remember the threshold of doubt, right? So as long as the belief is above half, he wants to convict. So when he sees a guilty signal, he will convict. Now, what happens if he sees an innocent signal? That's our second line, right? And there again, Bayesian updating will pull down the belief on guilt, the conditional belief on guilt, below 2/3, the prior. It so happens, if you plug in the numbers and calculate Bayes rule correctly, it drops down to 2/5, and that happens to be below half. So in this situation, the voter, the juror, the judge will actually want to acquit because the belief has fallen below the threshold of doubt. Okay, so optimal decision making rule in this scenario, when it's a judge, a single person making the decision, is simply informative voting. See a guilty signal, convict. See an innocent signal, acquit. Right? Simple rule. Now, the last remaining bit is, in this situation, what is the expected payoff? Okay? Or more generally, what is the probability that the judge will make a wrong decision? Okay? Now, the judge will make a wrong decision whenever his signal is wrong. And the signal being wrong has 1/4 probability. So 25% of the time in this example with a judge, the decision will turn out to be wrong. And whenever a decision is wrong, the cost suffered, or the disutility, is minus half. Remember, Q equal to half, so 1 minus Q is also half. So if you want to calculate the payoff, multiply that 1/4 by minus half, the cost whenever the decision is wrong. But more simply, let's just remember, as we move on to the next part of the example, let's just remember that the judge is going to be wrong 25% of the time. Okay, so now let us move on to the case of a jury of size 2. So there are 2 decision makers. They will cast their vote, and their vote will jointly determine whether the defendant is convicted or acquitted. Now, if you have 2 voters, then the voting rule has to be a unanimity rule. Either unanimity must be required for conviction, or unanimity has to be required for acquittal. So let's adopt one of these rules. Let's adopt unanimity rule for conviction. So you need 2 votes out of 2 to be for conviction, for that to be the collective decision. If even 1 vote is for acquittal, then the defendant goes scot-free. So those are our rules. Now, the question is, does this jury do better than the judge? Right? Now, one way to get at that question is to adopt the same rule that we saw for the judge. So let's suppose in this jury, each person just goes strictly by the signal, or does informative voting. So each voter sees a guilty signal, votes for conviction for sure, sees an innocent signal, votes for acquittal for sure. Suppose that's the case, okay? Then this expression that I have here is if you ignore the minus half, what we have in this bracket, in the square brackets, that's the probability of making a mistake by this jury of 2. Why is that? Well, with probability pi, the state is guilty. And if the state is guilty, they'll make the wrong decision. Well, they'll make the right decision if both get the right signal. Okay, both get the right signal, they both vote for conviction, and that's the right decision when the defendant is actually guilty. So 1 minus p squared is the probability that at least one of them will get the wrong signal and vote for the wrong thing, and so the wrong decision will be taken. So this first term is the probability that in the guilty state the wrong decision is done. The second term is the probability that in the innocent state the wrong decision is taken. 1 minus pi is the probability of the defendant being innocent, and in the innocent state, for a wrong decision, both of them have to get the wrong signal. Both of them have to get the guilty signal and vote for conviction. So that's why 1 minus p whole squared. So now you plug in the values, you make the calculation, you find that the expected payoff is minus 0.15 roughly, or a little more than 30% of the time, the jury will end up making the wrong choice, right? Either it'll convict an innocent person, or it'll acquit somebody who's guilty. And now if you compare with the case of the judge, you see that the jury, according to this calculation, is being wrong more often, right? The judge was being wrong 25% of the time. This jury is wrong more than 30% of the time. So that's bad news for Condorcet. Condorcet wanted to give us this message that larger decision-making bodies have an advantage over smaller ones, and that didn't work out in this example, right? So was Condorcet totally off the mark? Now, there's something I can say in defense of Condorcet at this point, which is that we just assumed in this jury of 2 with unanimity required for conviction, the jurors will vote as if they're still the judge, right? They'll adopt the same strategy that they would have adopted if they were the judge. In other words, they will engage in sincere voting. Now, that assumption is, of course, to be questioned, right? If the jurors are smart and they're rational agents, then maybe they will not behave as if they're still the judge. So let's check that. So the check that we want to do is whether or not both of them voting sincerely is a Nash equilibrium or a Bayesian Nash equilibrium or not, right? So let's assume that the other voter is voting sincerely, right? Guilty signal, vote for conviction. Innocent signal, vote for acquittal. If the other voter is acting like that, I as a voter, should I also act in the same way? Should that also be my strategy? And the answer is no. The answer is no. And that is very easy to check. And here is the check on this line. So, again, suppose the other voter is voting strictly according to signal. Now, I am, as a voter, I have received an innocent signal myself, right? So now I have to calculate the probability that I think the defendant is guilty based on my signal, and also conditional on another thing which is a little bit subtle, which is that the event that I am pivoting, right? Here's the concept. My vote only matters when I am pivotal, when which way I vote has an impact on the decision. So, for example, in this situation, if the other voter has voted for acquittal, then my vote doesn't matter, right? Because unanimity is required for conviction. If the other voter has voted for acquittal, then regardless of which way I vote, the decision has already been made. The defendant will walk free, right? So my vote doesn't affect the outcome in that case. So, as a rational player, I have to assume that I am pivotal, because that's the only situation in which my vote matters. In general, that means that the rest of the jury is kind of tied. So my vote will swing it one way or the other. So let's apply the concept here. So I, as a voter, am updating my probability of the defendant's guilt based on two things: my own signal being innocent and me being pivotal. Now, me being pivotal means that the other guy has voted for conviction, and given that I assume that the other guy is voting informatively or sincerely, that means that the other guy's signal must be G, right? He saw a G signal, he voted for conviction, and that is what has made me pivotal, right? Okay, so if you boil it down to its essence, this is a situation where my own vote is innocent, my own signal is innocent, and the other guy's signal is guilty, so these two cancel out, right? So that means that my posterior belief on guilt is the same as the prior belief, namely 2/3. And there's a typo here, the inequality should be the other way around. So 2/3 is greater than half. Okay, so what that boils down to is that if the other voter is voting sincerely, then I, as a voter, even if I get an innocent signal, I will not want to vote for acquittal, I would actually want to vote for conviction. And it's an easy check that if my signal was guilty instead, if it was G instead of I, then my belief on guilt would be even higher than 2/3, right? So if the other voter is voting strictly according to signal, voting informatively, then I would always want to vote for conviction, no matter what my signal is, right? So the best response to sincere voting by the other voter is to always vote for conviction. Okay, now, so that refutes this point that we made earlier, that the jury will do worse than the judge, it will be wrong 30% or more of the time. That conclusion rested on an assumption which on closer scrutiny turns out to be a very problematic assumption, that both of them will vote sincerely is not an equilibrium. Okay, so then we have to get back to the question that, in this jury of two, what is the outcome we can expect? What is going to happen then? So to understand that, what we have to do is actually find the equilibrium. On this slide, what we have shown is sincere voting on both sides is not an equilibrium. But then what is the equilibrium? Well, here's one way to try and find an equilibrium. We can look for a symmetric equilibrium. Okay? And a symmetric equilibrium will in this example will involve mixed strategies. So let me show you how to calculate that. Now, remember that the inclination is to vote for conviction. That's the direction in which things are tilted. So what we are trying to do is we'll try to find a mixed equilibrium of this form. So when the signal is guilty, the voters vote for conviction with probability 1. When the signal is innocent, the voter votes for conviction with probability sigma. So after an innocent signal, there is some randomization going on, but after a guilty signal, there's a clean vote for conviction. So the question is there an equilibrium of this sort, first of all? And secondly, if so, what is the value of sigma that will make it an equilibrium? Okay. Now, as you know, whenever you look at mixed strategies lead to an indifference condition. A rational player randomizes between options only if she's indifferent between the two options. So after an innocent signal, if a voter is randomizing, that means after an innocent signal, the voter must be indifferent between the two decisions, conviction and acquittal. And to be indifferent, her posterior belief will have to lie exactly on the threshold of doubt, namely Q. So what we're going to do is we're going to calculate this posterior belief, and this is the posterior belief we are interested in, probability of guilt, given that I'm pivotal as a voter and given that my signal is innocent, right? We'll calculate this posterior belief, and then we'll utilize this condition that this posterior belief has to be equal to Q. That is what is going to lead to indifference between the two decisions. So to calculate this posterior belief, we'll go in 2 steps, right? First, I'll calculate what is the probability of guilt given that I am pivotal as a voter before looking at my signal, right? There'll be some calculation. And then I'll add on this extra bit of information that suppose on top of that my signal is innocent, then what does my posterior belief work out to be? Okay, first step, probability of guilt given pivotality, right? So this is the Bayes rule formula. So where does it come from? Let's look at some of the components. Again, you should be quite comfortable with calculating Bayes rule at this point, but let's go through this. Okay, pi is the prior probability of guilt, first of all. So being pivotal can come about in 2 ways. One is in a guilty state, when the true underlying state is guilty. The other is when the true underlying state is innocent. So what is in the numerator is the joint probability that the state is guilty and the other guy somehow ended up voting for conviction. So when will the other voter vote for conviction? First, with probability P, he gets the right signal. He gets a small g signal, right, which truly reflects the state. Secondly, it may also happen that he got the wrong signal, but remember, when he gets innocent signals, he randomizes. With probability sigma, he still votes for conviction. So that's another way in which he can end up voting for conviction. Okay, now a vote for conviction from the other voter may also come about in a different way, where the true state is innocent, that is probability 1 minus pi. He gets the correct signal, that is, he gets the innocent signal, but still through randomization, that is with probability sigma, he ends up voting for conviction. Or the true state is innocent and he gets the guilty signal, that is to say the wrong signal, and then with probability 1 he votes for conviction. Okay, so this is Bayes rule. So you plug in the values, all the parameter values that we have taken, and you simplify and you get this expression, right? There's sigma in the numerator and the denominator. Now let's call this lambda. So this is like the interim probability. After learning that I'm pivotal, what is my belief on the defendant's guilt? So the next step, conditional probability of guilt given that I'm both pivotal and my signal is innocent, right? So that means I can start with a prior of lambda and apply Bayes rule again, right? So it's 2 steps. At the end of this, we'll take lambda to be the prior belief. And then I saw the signal innocent. What is the probability of that? Well, either the state is actually guilty and I got the wrong signal, or the state is actually innocent and I got the correct signal. Right? These are two ways in which this combined event, being pivotal and getting an innocent signal, could come about. So this is another dose of Bayes' rule, starting from lambda. So again, you plug in the values and you get this expression lambda divided by 3 minus 2 lambda, and that's the posterior probability. Okay, so now we come to the indifference condition, right? And then we'll work backwards. Indifference, the voter is willing to randomize after seeing an innocent signal if this posterior probability equals the threshold of doubt, which in this numerical example is taken to be half, right? So this expression lambda divided by 3 minus 2 lambda should be equal to half to give us the indifference condition. And that gives us a value of lambda which is 3/4. And if you go back to the first step, if you plug in lambda equal to 3/4 and ask the question, what does sigma have to be? You just solve a simple equation and you get sigma equals 3/7. So what we have done is we have found a symmetric mixed strategy equilibrium. It involves the strategy where after seeing a guilty signal, a voter always votes for conviction. After seeing an innocent signal, the voter randomizes between conviction vote and acquittal vote, where 3/7 is the probability of voting for conviction. Okay, so that was a little bit of work, but let's return to the question, Condorcet's theme, whether a jury does better than a judge. So let's use this equilibrium that we have solved to address that question. So here are the error probabilities. We'll calculate it state by state. In the guilty state, what is the probability that a jury playing this equilibrium, the equilibrium that we have just worked out, a jury playing this equilibrium, what is the probability the jury will make a mistake when the true state is actually guilty? That's our first line, right? Well, it can happen in, well, first of all, 1 minus the stuff inside the square brackets is the probability of making the right decision. So let's calculate the probability of making the right decision. We'll subtract it from 1 to get the probability of the wrong decision. So right decision can happen in a number of ways. First, both of them get the right signal. Right? The state is guilty, they get the right signal, both get the G signal, both vote for conviction, things are fine. Alternatively, one of them gets the wrong signal, namely the innocent signal, but still through randomization ends up voting for the right thing, and that probability is sigma, right? So 2p1 minus p is that one of them gets the right signal, the other gets the wrong signal, and then you multiply by sigma so that things still work out to be fine, right? Both vote for the correct thing. And finally, there's this third possibility that both of them got the wrong signal, but through randomization, both of them still voted correctly, right? So that's the last piece. So you plug in the values, including the value of sigma that we have solved for, and you get this probability 13 by 49. Now, what if the true state was actually innocent, right? And there, again, this is the calculation. If the true state is innocent, one way in which they can make a mistake is both of them get the wrong signal and both vote for conviction. Another way in which that can happen is one of them gets the wrong signal and votes wrongly for guilt. So that's the 1 minus p times sigma. And finally, both of them get the correct signal, namely the innocent signal, but still through randomization, both of them vote for the wrong thing. That's the third term in this calculation. Again, you plug in the relevant values, you get 16 by 49. Okay? So, what is the probability that in this equilibrium the jury will make a mistake? That probability will be the average of these two, because half the time the state is guilty, half the time the state is innocent. So it's the average, so it's like 14.5 divided by 49. And that works out to be 28.6%, right? And if you are calculating the payoff, you have to multiply that error probability by minus half, because whenever there's a mistake, the payoff is minus half. Okay, so now going back to the other numbers we found, the judge made a mistake 25% of the time. We are looking at a jury now, and the jury, once we allow the jury members to be rational and the jury plays a proper Nash equilibrium, even after allowing for all that, we find that the jury will make a mistake more than 28% of the time. So more often than the judge. Okay? So this example then shows that at least under one valid equilibrium, the jury's performance is worse than that of the judge. So again, Condorcet then is in trouble. Condorcet made the strong sort of suggestive notion that juries are better than judges, that there's some sort of wisdom of crowds. Okay, so bad news for Condorcet. But then if you want to defend Condorcet, if you want to really fight it out in favor of his wisdom of the crowds concept, what way can you defend him still? Well, one objection you can raise at this point is maybe we are selecting one particular equilibrium, right? Are there other equilibria where the worst performance of the jury is not true? So, is this adverse consequence a result of equilibrium selection? That's a question that we have to deal with. Well, turns out that yes, there are other equilibria, right? Some of these equilibria are a little silly. So for example, there's another equilibrium where both voters vote for acquittal regardless of their signal. So they don't even have responsive voting strategies, right? Why is that? Because if the other guy votes for acquittal no matter what, then I will never be pivotal. So my vote is not going to matter. So one of the things I can do, one of my best responses, anything I do is a best response because what I do doesn't matter. But one of the best responses I have is also to vote for acquittal all the time, ignoring my signal altogether. So technically speaking, it is a Nash equilibrium. You may want to sort of, you may not be very happy with this Nash equilibrium. You may think that it is unlikely or implausible, and you can make a case for that. But let's move ahead and let's try to find any other equilibrium that may be there in this simple setup. Or is there yet another equilibrium which is better than this silly equilibrium as well as the symmetric mixed strategy equilibrium that we calculate? And the answer is yes, there's another equilibrium that we can find, and it is an asymmetric pure strategy equilibrium. Okay? So let me tell you what this equilibrium is. One of the voters always votes for conviction in this equilibrium. Right? One of the voters ignores her signal altogether. No matter what signal she receives, she votes for conviction. And the second voter votes sincerely. Gets a guilty signal, votes for conviction. Gets an innocent signal, votes for acquittal. So one of them is voting informatively. The other one is voting totally uninformatively in favor of conviction. I claim that this is another Nash equilibrium. And it's very easy to check that. Voter 2 is always pivotal. If voter 1 is always voting with conviction, then voter 1 is basically passing the buck to voter 2. Voter 1 is implicitly saying, you decide, to voter 2. So voter 2 is effectively being made the judge, as it were, by voter 1, right? By stacking her vote in favor of conviction. So we know what is optimal for a judge, so voter 2 will act that way. So voter 2 is indeed playing a best response here. What about voter 1? Given voter 2's behavior, is voter 1 playing a best response? And the answer is yes, because we already checked that 2 slides back. We saw that if, remember I did the calculation, when one of the voters goes strictly by the signal, the other voter will always want to vote for conviction, regardless of what her own signal is, right? So that guarantees that both voters here are playing a best response to each other. So this is also a valid Bayesian-Nash equilibrium. So what is happening in this equilibrium? In this equilibrium, essentially the jury is mimicking decision-making by a judge, right? Essentially, voter 2 has been converted into a judge, right? So the outcome is just as good, no better, no worse, as the case of the judge. So 25% of the time, under this asymmetric equilibrium, the jury will go wrong, which is exactly the same frequency as the judge. Okay, so let's summarize what we have learned through this numerical example. What we have learned is, first of all, when you have 2 or more voters making a decision, it is tricky to find, what the outcome is going to be. You have to apply the game theoretic concept of Nash equilibrium or Bayesian-Nash equilibrium to figure out the outcome. And one thing we saw is that even in this very, very simple example, there are multiple equilibria possible, right? So equilibrium selection becomes an issue in these voting games. When we selected the symmetric mixed strategy equilibrium, Condorcet's conclusion did not bear out, at least in that simple 1 versus 2 comparison. The jury was actually doing worse than the judge. But there's always, there's this other equilibrium where the jury essentially mimics the outcome that would have happened under a judge, right? So if you're free to select the equilibrium that will be played by the jury, then Condorcet is kind of restored. Then, at least things don't get any worse when you expand the size of the decision-making body. Okay, so these are sort of, I ran through this numerical example to give you, first of all, a sense of how to calculate equilibrium in this case, and also a little bit of to give you some preliminary understanding of, in these voting games, what happens to the Condorcet conjectures, whether juries do better than judges or not, or what it takes, etc. One thing we have already seen is it depends a bit on the equilibrium that we select. Okay, so next what we will do in the next segment is we will sort of generalize on this numerical example. We'll study more general versions of this sort of voting game, and we'll address the Condorcet questions. So we'll look at the paper by Feddersen and Bessendorfer and by Austin Smith and Banks a little bit, and we'll really jump into examining the questions that were raised by Condorcet 200 years ago.